All right. Hello, everyone, and welcome to this final quant talk of the fall semester. So it's my pleasure to introduce Dr. Drew Winters, who holds a research faculty position at the University of Colorado Medical Campus in the Department of Psychiatry. Inspired by a clinical career conducting home-based interventions at the family and community levels, Dr. Winters pivoted to a career in academia to understand clinical problems that were not resolved at these broader levels of intervention. Though his work focused on fMRI to investigate individual differences beyond what we can observe at the behavioral level on the topics of social cognition and adolescent development in relation to persistent clinical issues. The popularity of fMRI data has grown exponentially in the past decade, and that makes for the consideration of statistical modeling a really critical topic for improving science and inferences on brain and behavior relationships. And so in this talk, Dr. Winters aims to build initial competencies that can make us all better consumers of neuroscience literature, and that can provide the basis for more advanced topics on neuroimaging analyses in the future. So thank you for being here, Dr. Winters, and I'll turn it over to you.
I'm asking real quick. All right, thank you. Yeah, hi, it's an honor to be here to present you today, and I just want to make sure I express appreciation to the Quant Family Collective for organizing this and having me speak on this topic. But for this talk, we'll be talking about fMRI data and some statistical approaches. First, just to place this in context, so I assume that there's limited experience with fMRI data, and I will be providing some basics while also speaking to those with some experience with this data. And I assume that you have some understanding of regression broadly. What I intend for you to leave us today is an understanding of what fMRI data is and what we're measuring, the types of fMRI data that you may encounter, and some approaches to statistically model fMRI data. The approaches we consider will be cross-sectional, but they can easily be adapted for longitudinal analyses, such as introducing approaches that were outlined in Dr. McCormick's presentation earlier in this session. To accomplish the goal of this talk, the structure will follow these topics. We'll start with an introduction to fMRI, set the base for considering what types of fMRI data you may need, as well as the statistical approaches to address problems that you're trying to solve. So let's start with just talking about fMRI data. So functional magnetic resonance imaging, or fMRI, is a non-invasive approach to study activity of the brain. During an fMRI session, a series of brain images are collected continuously that produces multiple reconstructions of the brain. But how does this occur? So this image here depicts the process to image acquisition, which involves the excitation of biological tissues placed in a strong magnetic field, and the recording of the recovery process from that excitation to measure structural and functional data. I'll discuss each step of this image to provide a broad overview to get a sense of what's being measured in fMRI. So first, the atoms composing the body's tissues spin with variation in momentum and direction. In fMRI, a powerful magnet is used to orient those atoms in the same way. Then a radio frequency pulse is introduced to disturb the direction of those atoms. The atoms of different tissues have different recovery times from this disturbance, and this allows us to detect differences in tissue types like bone from gray matter. Coils in the MRI record these recovery times, and from these recordings, we can reconstruct an image of the brain. This includes structural and functional data. Now for brain activity, fMRI is not measuring activation of neurons, but rather the lagged neuronal demands of those neurons. And we can observe this in the ratio of oxygenated hemoglobin in the blood. This is called the blood oxygenated dependent signal, or BOLD. In this figure, you can see different oxygen ratios for a given state. At baseline, we have about 50-50. At onset, there's a little less oxygenated hemoglobin, and at the activated state, there's more oxygenated hemoglobin. The changes are represented in this hemodynamic response function, or HRF, where we start at some base state, we introduce a stimulus, where after some delay, we see an onset of neural activity, followed by a peak in BOLD that rapidly declines and drops below baseline before fully recovering to baseline. It's important to note that the delay between stimulus to peak. Again, to reiterate, fMRI does not measure activation, rather the lagged neuronal demands. And many rightly point out this fact when anyone uses the word activation for fMRI data. And I'm probably going to say activation during this talk, so just know this is what I'm referring to. Okay, now when we acquire fMRI data, this is done in slices, much like you see here in this highlighted portion of the left-hand corner. Each of these slices is broken up into small 3D cubes called voxels, like you see here in the right-hand corner. A voxel is just a cubic portion of the brain representing a spatial location and some number indicating intensity for that voxel for the time it was collected. The smaller the voxel that you have, the better resolution that you have. In this example, you may see this red cube here that has kind of a rectangular shape. That's not as common these days, although it does still exist. Typically, they're in equally symmetrical cubes or isometric cubes, typically. Then these slices are stacked on top of each other and aligned to reconstruct a 3D representation of the brain each time point, which is known as a volume. So what you have is a representation of the brain with hundreds of thousands of voxels collected repeatedly over time, with the repetition time meaning the time it takes to collect the entire volume of the brain. And when you look at any voxel across all volumes, you'll have a numerical representation of the bold signal at each volume represented in a time series. So as you can see, functional fMRI data is a time series. However, this is a big time series problem. With approximately 100,000 voxels measured thousands of times for many participants, we can start to understand why storage capacity and high computing power is needed for this data. Often, data is simplified by parcellating across voxels using an atlas or mask. If you're not familiar with the word parcel, it's just something, it's very similar to using an average score for a self-report measure. But with an fMRI, we're averaging across voxels in a predetermined spatial location in the brain. So anyway, the takeaway here is that fMRI data is just a time series representing the bold intensity for a given spatial location over time. So I hope this sort of gives a sense of what this data looks like. I can pause here for questions, but if any time there's a question, go ahead and just kind of, you're welcome to interrupt and we can address it then. If there's no more questions here, I'll just kind of move forward to get a sense of what the types of data that we have. Okay, so in collecting or finding fMRI data, you're going to see the following. One is resting state data. This data is collected when participants are just sitting in the scanner. They're usually instructed to not do anything or think anything in particular. Their eyes could be open or closed, and some have them stare at a fixation cross like I have here. Because they're not engaged in any task, this is thought to represent trait-like patterns in the brain rather than task-evoked patterns. You also see task state data, and as it suggests, this is data that's collected when someone's completing a task, potentially something like the schematic that you see here. There are different design considerations for these tasks I'm going to kind of cover in a few slides, but because they're engaged in a task, it is thought to represent task-evoked patterns in the brain. Another growing form you may see is naturalistic data. This data is collected when participants are listening to a story or watching a movie clip. Because they're engaged in a passive activity, it is thought to represent patterns similar to what we do naturally. This data is thought to be more controlled than resting state data, but less prescriptive than task state data. So for a little more detail about resting state data, this is most commonly used to examine how the brain is functionally connected. This is based on the Hebbian principle that neurons that fire together are wired together. So when we see a similar bold signal in two regions of the brain, we consider these regions being connected. As you can see in this figure, the time series between these two separate regions appear to move in a similar fashion. There are some modest differences in intensity, but we can visually detect there's likely a positive relationship between these two nodes. This relationship is typically quantified with a correlation value to represent the relative similarity in bold for two or more regions. And graph theory is often applied to represent these connections, resulting in a large correlation matrix. Like this figure here, we see a heat map representing correlation values for every region of the brain. Now, the same figure can be represented in a number of different ways. This makes for great figures. In these below, each line is called an edge, representing the strength of relationship between nodes. And it's important to note that the red values indicate positive connection, whereas the blue values indicate a negative connection. The positive or negative connections have important distinctions. Where positive values suggest two or more regions are working together, negative values, or anti-correlation, suggest that one region is active when another is not. This is represented in this figure where you see the time series are opposite each other. This may indicate separate computational properties of regions for a given process. Here's an example of what patterns of connectivity are expected at the network level. The Salience network signals switching between the default mode and executive networks. The default mode network is task negative, meaning it's active when we're not doing anything in particular. And the executive network is task positive, meaning it's active when we're engaged in a task. So we expect the Salience network to positively associate with default mode and executive function, or executive networks, but the default mode in front of parietal to anti-correlate. And disruptions of these patterns is a popular brain model to study mental health. The strength of resting state is that there's not a lot of design considerations that can help us understand functional architecture independent of a task, and many have found these patterns to be reproducible. Criticisms is that, well, no one knows what each individual is doing. So if someone is kind of having some more positive thoughts and some are having some more negative thoughts, that could influence what's going on in the scanner. But on the other hand, such patterns or tendencies may better characterize a phenotype of interest, so it may be a feature, not necessarily a bug. And there's lots of debates on amount of time in the scanner to be reliable. 10 minutes is often used, but some suggest more, including some with multiple sessions with substantial time. A lot of work from Katrina Grattan discusses this quite a bit, but really it all depends on your research needs and what you're trying to accomplish. All right. One more detail about task state is that these experiments have important design considerations. Specifically, we need to consider the recovery time of the HRF that we outlined earlier. Because if we were to have rapid stimuli like you see in some behavioral tasks, you'll see the HRF plateau rather than the full HRF. Now, this may be fine depending on what you're doing, but it needs consideration. Primary designs for task state data involve either a block design or event-related design. The block design is a block of stimuli producing an elongated HRF. Now, this is useful when you have a specific condition that you want to compare. You can easily extract the different conditions and compare them. And this design is excellent for knowing which voxels are active and examining state changes, but it's not as great at knowing the time course of an active voxel because this design is insensitive to the shape of the HRF, given we're not allowing the recovery time in this design. The event-related design has space between each stimuli, allowing for recovery. Now, this is useful when estimation of a time course for an event is important. So this is excellent for knowing the time course of an active voxel and examining state changes as well, but it's not as great at knowing which voxels are active because it is sensitive to errors in the predicted HRF. These designs can be combined with blocks of event-related designs as well. But task state data is usually used to reveal changes in activation of brain regions. In this study by Arwich and colleagues, it examines activation of the right anterior insula in 3 different conditions. So the right anterior insula is defined graphically by the application of a mask, and the time series across the voxels is represented in the red regions that are parcellated together. These voxels are averaged in 3 separate conditions that are compared statistically, usually with a t-test, and just on visual inspection, it appears that there are main differences across conditions. The strengths of task state data is that we're able to investigate brain response to specific tasks. It's great at predicting brain responses and localized activity to a given process. Criticisms are that there's a question on ecological validity because it's thought that it's unnatural to do tasks in fMRI. Many question if this is generalizable to behavior outside of the scanner. And these experiments are sensitive to task parameters. In some cases, small modifications can result in differences in the result. More about the naturalistic data is there's some unique considerations here. So having participants just watch a short clip can appear simple. However, stimulus properties fluctuate rapidly, which can have different impacts. So here we see a time series of changes, including luminance, existence of faces, and the emotional valence of that specific clip at that time. And these interact with observer properties, including their salience detection, their heart rate, and their personal experience of joy, which can dictate brain activity for a given region or network. So while this allows many opportunities in studying the brain, we have additional considerations such as how to model the data and how do these fluctuating properties impact interpretation. Methods with this data are still developing, and so I'm gonna leave it for now, and if that's an area of interest, that can always be revisited. Okay, so strengths of naturalistic data is that it's considered ecologically valid because we're doing something that we would do even if it's outside of the scanner. We know what people are doing, so it's more controlled than resting state, and we can examine brain patterns during a passive activity. Criticisms are, and now I just want to point out that we can methodologically reduce the impact of these with some packages and other areas of help, but it is challenging to model brain responses to given stimuli. Even with the same clip, it's not exactly the same for every participant. The timing's a little bit off, and the flux and flow of bold is sensitive to the HRF estimation error because the events are not tied to a condition, and it's not repeated to improve accuracy of the bold response. And this makes it sort of difficult to compare. And brain responses are sensitive to characteristics of the stimuli. The constant fluctuation of stimuli features, something that can't be controlled like we do in a task where we simply have similar parameters and they're presented with the same stimuli repeated times. And same with resting state, there's debates on the amount of time in the scanner to be reliable. Okay. So now just kind of having a sense of what kinds of data that we have. I'm just going to talk briefly about how to form a hypothesis with this data. So as Dr. Rajiv expertly pointed out earlier in the series on forming hypotheses, we're going to use many of those principles here, but the only addition here is that we're modeling brain data to test our hypotheses. So the first step is to define what about the brain you want to know. This involves defining what about the brain can help you understand your studied topic. Many times we get very excited about what the brain's doing, and this is a step that's skipped sometimes, particularly when people first start getting involved with this data. So it's a very, very important step. And there's a couple of considerations. First is fMRI data necessary? The reality is that this is expensive to collect. So consider, can you answer your question without fMRI data? If you need it, you're really going to need to convince others it's necessary. For example, if you want to inform an intervention, why not just do the intervention and skip the brain data? What about including brain data will improve future intervention work? So those are things you need to convince others of if you're writing a grant. Next, what brain properties are critical to your question? So the brain can be modeled in a number of ways, but it needs to answer your question. And you may want to consider if you need to know whether activation in response to a state is important, or if connectivity, whether at rest or during a state, is important for your question. Next, how will you model your data? For example, can you assert the brain is homogeneous? If homogeneity is assumed, in a very strict sense, you're stating that all individuals in a group have identical brains and estimate weights. You might adopt a strategy if you believe all brains are the same and you're willing to give up statistical power, or if your question only wants to understand mean differences between groups and you can comfortably go to bed at night imposing assumptions of homogeneity on your data. If homogeneity is tenuous, you adopt that there are individual differences and you want to examine what is similar across heterogeneous brains. You can adopt this approach if you believe brains are heterogeneous and you want to retain power to detect nuanced associations, or if you want to bolster confidence in your estimates. Next, we use a brain model or examine the whole brain patterns. There are strong feelings by some on both of these approaches, but it depends on your field and where brain research is at in your area. So some argue that whole brain studies lead to spurious findings, and there's many examples of that, while others argue that only looking at a specified brain model biases the results. Your knowledge of your field will kind of guide your decision here. So for example, if there's hundreds of studies doing whole brain analyses and about 90% of them identify a model specific to your area, you might want to consider building on prior work to advance your area of science and use the model. Just a point of consideration. But answers to these will inform how you approach data analysis, and I'll cover some potential approaches. So in this section, we'll just briefly cover critical components of analysis before going into a demonstration on these concepts. With some exceptions that we're just not going to get into here, modeling fMRI data generally occurs in two steps. The first involves modeling each individual participant's bold signal, and the second step involves examining brain patterns across participants to make statistical inferences or predictions. So we're going to cover the conceptual components of these here before going into the practical application. Okay. First level, individual bold estimation, is a necessary first step that allows us to extract brain properties that we'll use to test our hypotheses at the second level. This initial step looks different for different types of data. So for task data, we want to use the task-related events as a model for what we will expect the fluctuations in HRF to be. Right? So we map or convolve the known events during a task with the hemodynamic response function and use this as a baseline model for expected bold in an individual. So this is typically done with a generalized linear model. During the demonstration, this is the approach that I will cover, but there are other approaches that I'll point out as well. For connectivity, on the other hand, we want to model the magnitude of similarity in bold fluctuations for each individual. So in other words, we want to know what regions are correlated, uncorrelated, and anti-correlated. There are a variety of ways to estimate this, but the most common approach is Pearson correlation. So with these individual level bold estimates, we can then move into examining patterns across individual ranges. So at the second level, we use the individual bold estimates to examine patterns across participants to tell us about a group, phenotype, or behavior. This can be done such that a given stimuli can tell us about brain patterns, or called encoding, you see at the top of this figure. Or we can use the brain to tell us about behavior or response to stimuli, called decoding, you see at the bottom of this figure. Now, I just want to note that decoding requires careful consideration, so we need to be very careful about how we get the identified brain patterns or brain model that we use. How is that derived? Right? We also want to be careful about the methods that we use, and we want to ensure that we're not making a logical fallacy like affirming the consequent. Right? So, for example, if one says amygdala activation equals fear, we know that's just not the case, when in reality there's a number of different experiences that the amygdala may activate, right? So sort of simplifies it and affirms the consequent, making a logical fallacy. We don't want our models to be spurious. It'd be ideal if it's replicated, whether it's across your field or where that may be. And methodological applications of this typically involve machine learning approaches in order to do this decoding component, but there's some examples of inferential statistics that have done this as well. In this example that we have here, they use reaction time during tasks to predict bold fluctuations of 3 separate nodes. So essentially, they're trying to infer how behavior can tell us about brain responses. And these are the basics that we're going to cover in more detail in our tutorials, which we'll get to now. Just a little bit of introduction to the tutorials here. I hope to get through first level and second level analyses for both task and resting state data. If we do or not, or if you'd like to review, you'll have these tutorials available to you so that you can go through them at your leisure. I try to provide enough detail in these tutorials so that you don't need me, but that may not always be the case. Regarding code, I use Python along with an easily accessible format called Google Colab, which allows you to run the code on your browser without having to download anything. However, you do not need to run the code, as I've done that already. The purpose is just to teach you, the purpose is not to teach you how to code in Python, but rather to demonstrate these concepts. So we'll focus on the results of the code. If you want to learn the code, you're welcome to dig into the code outside of the presentation, or check out free coding resources like Software Carpentry. I will also just say that analyzing fMRI data typically is done in languages like Python or MATLAB, rather than R or other languages you may be familiar with. Additionally, most of this code is for demonstration purposes. It's not necessarily the real world approach to conducting full analyses. So the purpose I have for this talk is to grasp the concepts that I could build on later if everyone wanted to extend or look at more advanced analyses. So I'm going to exit the presentation and open where the repository for the demonstration component is. And I don't know if this link has been provided in the chat or if it hasn't, somebody could. If you want to look up github.com/Drew Wendt, Quant Family Collective, you can see the repository in my GitHub here available to you. You should see something like this. We have 5 different workbooks relevant for this presentation that we're going to work through. Now, if you click on one of these, I already have it open here, you'll see on the GitHub page itself, you can just kind of scroll through. You see I already have the results up and all the figures and things like that. You can, if you want, open in Google Colab, this little button at the very top of it, where it'll take you to a screen where you can run the code yourself in real time. That's up to you to do. I'm going to remain on the GitHub page itself, just because I already ran the code. I'm just demonstrating purposes of this, or the content at this point. And yeah, let me do that. It looks like someone didn't send it yet, so let me just send a link in the chat myself here. Okay. Thanks. Point that out. Jordan, okay. Yeah, so it should be in the chat now for you if you just want to click on it. Okay. All right, so that being said, we're going to start with task individual level. We're going to move into at the individual voxel level to demonstrate concepts before we move into whole brain stuff. And then we'll do resting state, individual, and second level analyses. So here, this first tutorial here, this is first level estimation of an individual's fold for using task stimuli. And for demonstration purposes, we're only going to focus on one voxel here, but we'll expand on this in later tutorials. So to do this, we're going to convolve our task events to an HRF and predict the individual's fold for that one voxel. Again, we're focused on GLM here, which is the most common approach, although I want you to be aware of other methods such as maximum likelihood or Bayesian approaches. And I provide some links in this tutorial that may be helpful if you want to explore those approaches more. So this is pretty much summed up in this image here, where we take the events that we understand are going on in the task, and we map it onto the expected HRF in order to get our model of what we anticipate to be the case given our task parameters. We'll start with convolving. Now, this first example is just a very basic example, just to get the concept of HRF task parameters together, and we'll move into maybe a little more realistic example. So first, we estimate our HRF, this line of code here, and you see this very smooth line. This is probably familiar from the initial introduction to this talk, where I talked about this in more depth. But this is kind of a idealized version of an HRF. It's very smooth and nice, and that's typically not the case. So for the purposes here, I'm going to just not oversample as much so that we get a little bit more of a rigid looking HRF, just to kind of simulate what it might look like more in real time. So we take this HRF, and we're going to map it onto a series of stimuli that we depict here, where we say, hey, there's 5 stimuli series within this given time frame, and they occur at these different intervals. So we're going to map this on to there in order to get an expected HRF function called convolution, right? And throughout this, I have various equations here if you want to take a look at them. And I tried to indicate what each of these aspects of the equation mean. I know sometimes it can be frustrating to look at an equation you're not familiar with and not know what each of those are. Hopefully that's helpful. But anyway, so we have our stimuli series here, and we just convolve that with our HRF, and we get something that looks like that, right? So this is an idealized expected version, right? And this is a very simple task, not something we typically would work with. So let's consider a design where we have presentation of faces and presentation of objects, and we're going to sort of compare those. So instead of just the 5 time series that are nameless, we're going to estimate, or we have here the stimuli for face and for object for one task here. And at this stage, what we're first doing is we're simulating maybe a more realistic looking time series for an individual that you may get if you just pull raw data from an fMRI experiment. So I've taken the liberty in this case to say, hey, I think that face will have greater activation than object. And then we convolve that with our expected HRF and we get something that looks like this. But this still isn't like what we would see in a real fMRI time series. Right? This is very neat and clean still, some jaggedness to it, but typically two things. One is there's a lot more noise between these, and two, we don't really have the separation of face and object when we get a time series from an fMRI. We have to use our GLM to predict that. So we got a little bit of noise here, and this is something more realistic looking, what you may see from an fMRI experiment. And again, we have these two conditions, so we'll just add them together to make one time series. Now, this is our time series that we're going to use to predict in our GLM. Right? We're going to model our expected HRF for the different conditions and try to see how can we recover the signals that are meaningful for us using GLM. So to do that, we construct a design matrix where we say, okay, we know where the stimuli test parameters are at, or where the stimuli presentations are at. And we're just going to map that with our expected HRF, right? And we have some constant. So I just have a constant value here at the top. And when we try to make it look like a typical regression model, we see our time series that we created here. It's singular, right? Just one constant flow. We have our intercepts, we have our faces, we have our objects that we're going to try to extract or recover the meaningful signals from this time series that we got from this experiment. Okay, and we do this by estimating GLM, as I talked about earlier. And here's some links for like Bayesian approaches and some GLM estimation overview if you want to get more details. Presented by Torwager and Martin Lindquist, a very good job there. And in this instance here, you typically won't do this, but I've developed, I've sort of written some code that mimics the equation that you probably are familiar with if you've ever seen, taken a regression course before. This is what it looks like in Python code. You typically won't do this. You don't need to do this, but this is just for demonstration purposes. So we define this estimator here. I take our X, our design matrix, which is this, right? These independent variables here on Y. And then I extract the predicted Y and I stack those together to make a predicted time series. That's it. But now we want to sort of evaluate it a little bit. Typically don't go into this depth in a real world analysis, but it's not, you always want to check your data. And there's other ways of doing this that we're not doing here. But demonstration purposes, let's look at the time series we recovered. So this blue one here is the predicted time series that we recovered, right? This is what we have. Here's our simulated time series. And you'll note that we recovered these higher peaks in the face components while retaining the maybe somewhat blunted peaks for the object components. And what we didn't extract here is all this noisy stuff that we didn't expect, right? There's a lot of jaggedness there that maybe wasn't anticipated. It's not tied to the stimuli in any way, shape, or form. So it looks like we did a pretty good job there of getting what we want and not retaining what we didn't. If you looked at what's left over after we, left over from the model, you can see the peaks are pretty well taken care of. So we seem to retain the signals that were most meaningful for our task there. There's other various ways to sort of evaluate your data. Residual errors is a good way to look at it. One of those closer to zero. R-square may be one that people are familiar with. And here's a subset I did here if you want to go into more detail on that. But we have a R-square of 0.61. It's pretty good. And then we have, you can always evaluate our estimates and see what's different between them for this one individual. But this is just one individual for one voxel. So we're not making inferences here. We're just kind of seeing like, how did this GLM do at this point? But overall here, that just kind of, hopefully that gives some intuitive sense for what we're doing at the individual level for a task, right? For the first level, right? We want to take this estimated bold signal and use that to make inferences across participants. And we're going to follow a similar example in the next tutorial we're going to do the same sort of a thing, only with multiple participants. And we're going to use some contrast or make some design matrix with contrast just to kind of demonstrate those components. So if you want to click on the next one here, it's the workbook 2, second level. We're going to take the same approach from that single voxel to that single participant to examine patterns across participants. This is often called a second level analysis, and we'll start with the first level GLM again here and just kind of skip through that very quickly because we already did that. And then we'll run analysis across participants, define various contrasts, and I have multiples of these. I'm not going to go through all of them. I think at some point it just gets repetitive, but there's multiple different contrasts you can kind of consider and think through if you want to look through this tutorial again later. So to start with the first level estimation, we do the same thing again. I did create a function here that's helpful. You can look for that if you'd like, but we do 5 different participants here. So simulate 5 different participants. And this is our expected model, right? And this is what each individual looks like. Now you'll notice that we have similarity here, in as we would expect, but we also have a lot of different differences in magnitude and the way they respond to those stimuli that we simulated. So we're going to take this, and we're going to, again, for the individual level, again, we estimate our first level, we get our betas for each, and because of the way that we set this up, the first one is our intercept, second one is our that's our faces, and our third one's object. So I have it stacked here if you wanted to check that. So intercept, faces, object, intercept, faces, object for each participant. And a quick valuation here, look in the mean squared error, the residual. These are all pretty small, so I'm not going to dig in that too much more. What we do at the second level, so the way we design this here, is we want to take these predicted values, and in this case, you can stack them in different ways, but in this case, we stack them such that it goes faces, object, faces, object, faces, object for participant 1, participant 2, participant 3. So there's 2 values, each one for each participant that's stacked on top of each other, and we have that here. Okay. Just quickly about contrasts. So being familiar with regression methods, probably familiar with seeing an equation like this. We have our intercept, our beta 0, beta 1 is, here it's faces, and beta 2 would be objects, right? We can weight these in different ways in order to get a linear combination that tells us about what's going on and why, right? For example, if I wanted to know what's the activation in faces relative to objects, I could weight the faces at 1 and the objects at 0, much like any dichotomous variable, and we get a sense of that. Or I might want to know what's different between faces and objects, and I would weight objects at -1 and faces at +1 in order to get a sense of what's different between those 2 betas there. I'm going to demonstrate that a little bit below. I don't know if this is helpful or not, but I just sort of did a figure of what the intercept is here, obvious 1, right? And I have the face time series. You can see there's zeros throughout, except for when faces are expected and when objects are expected. So that just kind of gives an idea of what's being contrasted there. I created a rather large function. If you're doing this in the Google Colab, this is kind of hidden, but if it's directly on my repository here, you're going to see this big log function. Hopefully this is helpful. This took a lot of time to edit, and hopefully it makes it clear. If there's any thoughts on that, but for our first contrast, we're just going to say what's going on for each individual contrasting face from the object activation conditions. I wrote some stuff here that may be helpful, but I think it's just easier to just dig into what the actual matrix looks like here. So we have our Y value, and we're trying to extract a linear combination of a difference between these two for individual 1. This is 0 because if you're not familiar with Python, it indexes at 0, whereas some other languages index at 1. So this would be the first participant. We have our contrast here. So this is the beta naught that we're interested in. And we need to tell it also that this is for this participant, right? So we're indicating 1, 1 here. This is participant 1's face and object values here. We're going to contrast between those, and you'll see that's the case across participants, right? This is what it looks like graphically. These are what the Y's values may look like graphically. This is the graphic of, the matrix I just have up here. We have our contrast here, 1, -1, 1, -1, 1, -1, right? So we're comparing, we're seeing what's different between faces and object conditions for each participant. And we're looking across those participants. The result looks like this. So we have a number of beta values, or beta naught, beta 1, 2, 3, 4, 5. And each beta here, the 1 through 5, is just the individual's mean. Because if you look at this matrix here, we're just saying this is this participant, and it's going to the regression finds the best linear combination between these two values of y, right? So that's just participant 1 mean, etc. Right? This beta naught, this contrast, this tells us what's different, right, between these two conditions across all participants. And here at the second level that I have outlined here, we have a significant difference. Now, what's different? Well, in what direction would you want to interpret it, right? Well, if you look at the values, the face voxel beta is mean, the object voxel beta is mean. We see that there's significantly more here going on with the face voxel betas, right? So we could say that there's, seems to be a higher activation that we're retaining from the face voxel across all these participants relative to the object voxel betas, and there's a significant difference between those. Okay. I do add here many more details on what each beta means, and so hopefully that's helpful if you're looking at this, not during this presentation. I just put a regression table here because people might like seeing this format better. So there's that. It's the exact same values. You can compare these to what's going on up here. This might be more familiar to people when they're looking at results. So that's that contrast. You can also move into group contrast. So in this instance, what we do is we're estimating groups, right? So that's what all this code's doing here. Just estimate some groups, and I stack those in some list here that we use in our subsequent analyses. And if we were to wait, if we just wanted to understand, right, here in this contrast, or this design matrix here, we just want to know what's going on with group 1 relative to group 2, right? So all group 1 is weighted at 1, and all of group 2 is weighted at 0. We're not comparing conditions at this point. Just want to see if there's mean differences in just what went on in the fMRI experiment in general. Again, our betas here. This first beta, this is just the intercept, right? Our beta 1 is telling us what's going on with the first group relative to the second group that we're comparing, right? That's the group of interest. And as you see here, group 1 minus group 2, we have the same value here. So this is just a point of interest for trying to gain an understanding of what these betas look like here. That's why I provide these first level things here and all of these different contrasts that I have here for us. We can do the same thing if we want to say like what's going on with faces relative to the object conditions across groups, right? So we do the same thing here, and you can look at these betas, but we can also include contrasts, right? If we want to know what's different, so we would include a contrast at that point. And I have a number of different design matrices here that you can dig into, and I provide a lot more details on each of these. I feel like if I go through each of them, it's just going to be repetitive at this point. But this hopefully just provides a graphical representation for you to kind of get a grasp of what we're doing in these design matrices to get an understanding of second level analyses across brain patterns that we predicted at the first level. Okay, so all in all, let's go back up. Hopefully this gives you a sense of one voxel for multiple participants we have here, and just trying to understand patterns across those multiple participants for this one voxel for this one task. But obviously we want to extend this and go into what's going on across an entire brain, right? So our next tutorial here that I'm gonna go through is just doing the same sort of thing, but across every voxel of the brain. It's gonna be a lot easier because we have helper functions that allow us to do a lot of this stuff without having to look at all the weird functions that I made and try to decipher the code that I did there, which is nice. Hope you find this easier. So let's just go ahead and apply this to the same sort of analysis approach across the entire brain. So there's a lot of technical stuff in this one here that I'm not going to go into detail on because it'll sort of take away from the goal of the talk, which is to provide more detail on the concepts of these analyses. Okay. We're going to compare two conditions in this example where participants are presented with either a vertical and a horizontal checkerboard. As you can expect, looking at a checkerboard isn't a demanding task in many other ways other than your visual field. So you're going to see a lot of visual related activation, typically in the occipital cortex. Okay. So that would make sense. So we're going to compare those two conditions. And the technical part of it is we're going to download 16 participants. You can look at how I did that there and build a design matrix. Just run a couple functions that are helpful in NiLearn to sort of extract our analyses at the first level and second level. And we're going to plot those in many different ways. We're going to include some thresholding, some non-thresholding, and we're just going to kind of see what's going on with the data here in these different conditions. Okay. So to start off here, we download the data, and here's just where I made sure that, hey, these participants are the same. I did this visually without doing a test, just so that you could see that as well. And we download our data, and we are taking their downloaded data and we're stacking those in a way such that it's a condition, the vertical condition, the horizontal condition, and we're not interleaving them in a way so that it's participant 1, participant 2, participant 3, it's participant 1, participant 1, so they're stacked on top of each other. You'll see that here in a second. We develop our contrast. We don't know what's different between them, so we have ones and negative ones. And this is just identifying the participants that you'll see in this figure here, what I'm talking about. We have our vertical condition up here, 1 and negative 1 for our contrast. Participant 1, we have our vertical versus horizontal condition for each participant, so that we're comparing those in our design matrix here. And we're going to import that into this function called second level, where we fit that model in order to extract our analyses that we'll plot here in a second. Okay. So in plotting these results, at first, before plotting the z values that we typically extract and we'll compare, because z values are in a standardized space that we can compare across participants. Here I'm plotting the effect size, and this is for demonstration purposes, just to see where we may see the most meaningful activations. And we'll use this as comparison when we look at our z values for the threshold and the unthresholded maps. So as you can see in the effect sizes, we're seeing some stuff going on here in the occipital lobe area related to the checkerboard, right? Which is expected. So we have the highest negative values here in the very back, and there's this little central portion here that seems to be rather positively associated. And then there's a lot of variation, probably more in the middle ranges throughout the rest of the brain. So keeping that in mind, let's plot our z values. It's unthresholded across the entire brain. And you'll see, kind of compare them here. We can see that, yeah, we can see these activation patterns, but I don't know that I would see those if I didn't plot this first, right? This seems a lot of noise. It's hard to see what's most meaningful from this. So we're going to apply a threshold. And I did this a little bit out of order here. In this section here, I calculated the false discovery rate for the whole brain. And we have a z-value cutoff here of 0.378, which is, if you look at any z-table, z-score table, is a little bit higher. But that makes sense because we're looking at every voxel across the brain. We haven't limited our search at all. So there's a lot to correct for as far as multiple comparisons. And we apply that threshold. We see, hey, looks like we have something approximating what we'd expect is the most meaningful activation patterns, and we got rid of a lot of that noise, right? There's still some stuff up here that maybe we wouldn't expect, or maybe those are meaningful in some way, but these three here seem to be retained. They're much smaller than what we would expect from this effect size one. Not to say they need to be the same, but there are some differences. And part of this is that we've reduced a lot of our statistical power by looking at every voxel across the brain, right? We've had to compare for a lot more multiple comparisons. So one approach that you could take if you want to increase your power is say, hey, I understand that this is primarily a visual task. And while there may be activations in other regions of the brain that are meaningful, we really want to know about the visual spectrum. So here's some more technical stuff where we download a mask from NeuroVault, and we're going to apply that to our data. Now, these may seem meaningful at first. I'm going to skip over these. This is just a number of steps that I took to download a mask from NeuroVault and create it, do some manipulation to it to make a mask. And this is the mask that's created. So we have these white regions are where we're limiting our search to, right? Versus the whole brain. And this will allow us to sort of hone our search to areas we think will be most meaningful for our given task that we have, to maybe have a little more sensitivity to what may be important for the contrast between these vertical and horizontal conditions. So we apply the mask, we run our stats. If you're interested where the mask gets applied, it gets applied here in our second level model here. And then we plot it. And then you'll notice, we've limited our search here, right, to just these areas that are pointed out by this checkerboard mask from NeuroVault, right? But we still don't quite, we can see these areas here, but I don't know that visually I can really detect what's most meaningful from these yet still. So let's try to apply our FDR threshold again. This time the FDR threshold is a little smaller because we've limited our field. We don't have many multiple comparisons to correct for. When we apply this, we see that we retain this signal similar to what we did before, only we have a little more richness to what that looks like, right? We have this cluster here, these clusters here. We have a little bit bigger positive activation cluster here. So that may be something you want to consider if you want to try to extract what's most meaningful for your task. We can take this data. We can extract the clusters that seem to be most relevant using this get clusters table, where we get a list of the peak statistics and their coordinates. And we can take these, look at neurosynth or other related tools that we have to look up coordinates and see what's most meaningful about those, how they may relate to each other, or create a mask, and we can upload that into NeuroVault, much like the one we just downloaded. We can decode that mask across the literature for sort of like a meta-analysis kind of a thing, just to kind of support our findings, or allow other researchers to use them if they want to investigate the same sort of phenomenon. So these are just what's available to you and things that you could do across the whole brain. Here's another sort of a map that you may see, right? Some people maybe don't like the glass brain that I have here, and they like this more realistic looking brain, I guess you would call it. So I have it here available to you too. So all in all, that's kind of what every step of the analysis would look like if we're doing a whole brain analysis with real data for task state, right? We took the expected events within a experiment, and we mapped our HRF to predict the individual bold, and we looked at for patterns across that bold, right? We contrasted the different conditions that we expect within that task state. So that's what we do there. Things are a little bit different when we think about connectivity, right? We don't want to map our, we don't have task demands or events within the experiment in order to map our HRF to and try to understand the different states within that task. So let's talk about that a little more. Here at the individual level level, we're going to start with this, and we'll do the second level across groups next in our next one. So for resting state data, this individual level, right, we're just estimating relative similarity of bold fluctuations. So this can be done in a number of ways. What we're going to focus on in this tutorial is we'll look at the whole brain, then we'll look at network specific, and then we'll look at seed to voxel. So we're going to do one participant here for these stages, do more in the next tutorial. But this is kind of a good schematic of what this looks like here, where we're, for the whole brain at least, we're going to apply parcellation, extract the time courses, and see how they relate to each other. Whereas with the network specific and the seed to voxel, we'll define a region, create a sphere around it, extract those time series, and see how they relate. Okay. We're not simulating this data at the for resting state, so this is just another thing where I'm downloading data here, and I'm applying a masker, which is just there's a number of different atlases that you can get from the literature and apply to your data in order to sort of simplify it and look at quantitatively defined regions that are relevant for your study. Okay. So we do that here, but instead of extracting certain regions, we're just going to do a whole brain connectivity. Where we do that here, it's very simple. We just say, hey, we want connectivity measure correlation, it's just Pearson, and we fit that, right? So we have this correlation matrix, and then we're just going to plot it in a heat map. What we have here, right? We have a lot going on. Almost every voxel has something going on. There's a few here more in the middle with the white, but we have a lot going on there. You can take this, and if you add the coordinates, you can actually plot this in the brain, just like here. So we have the same correlation matrix. We just add the coordinates of where that is to be expected so that it knows where to plot each node in the brain. This looks pretty noisy, right? It's hard to know what's going on here. So again, like I talked about before, you can apply a threshold. And connectivity, this is typically done in a rather arbitrary way. In this example, I just say 80%, see what's different about it. And we retain most of these positive signals and only a few of these negative ones from that. But as I say before, just an arbitrary cutoff of like 80%. We could apply an FDR correction to this as well, or something to that degree. But there's other ways of estimating versus just your typical Pearson correlation. So some people have taken like a more principled approach using a specific type of estimator that allows us to induce sparsity and retain only the most meaningful connections without adding an arbitrary nature of selecting where you want that threshold to be. And one of those is graphical lasso. We're doing the same thing as above, only now we're calling this graphical lasso estimator, and we plot it just like we did before. And you can see there's quite a bit more sparsity here, and the values are a little bit different. There's a number of reasons for this. Specific to this estimator, if you have questions about this specific estimator, I can talk about that in more detail. If you're familiar with the machine learning literature, you may already be kind of familiar with it in a way. But we can see that there's some sparsity introduced here. And we can, again, plot this on the brain. And if you compare our graphical lasso estimated matrix or connectivity here to the covariance one, this one has some lighter colors to it. It's just because there's so much going on here. There's a little bit of sparsity here from the graphical lasso estimator compared to that one. It isn't to the degree that this 80% is, right? So that's just interesting to kind of have in your mind as you're considering how to estimate connectivity. And there's plenty of other estimators out there, some that are much better. This is just for demonstration purposes at this point. They have different uses for different functions and what your question entails. So that's kind of whole brain at the first level, right? We're not comparing across participants yet. There's one participant. So that's whole brain. We can move into deciding on just one network. In this case, we're going to use the default mode. We are using connectivity. Default mode is pretty prominent in resting state data. And we do that by defining the coordinates that we have here. You don't have to do the labels, but I have labels here as well for what those coordinates are. And we're going to create spheres around those to extract the time courses from those voxels within those spheres. And we're going to see how they relate to each other. So we apply these chords similar to what we did, the parcellation we did before. extract those, and we're just gonna, at this point, look at the time series of those extracted nodes. And as you can see, there's differences here, but they seem to move in a similar direction in a lot of ways. It seems kind of noisier here. This looks almost perfect, like everybody goes up at the same time and down at the same time. So all these nodes seem to relate to each other pretty well, as we would expect. The default modes are pretty well defined canonical network. So I'm just going to fit our correlation measure to those, and then we're going to plot it. And you see here, we have our nodes that we defined, different locations, this default mode network, and they're all positively correlated, which we would expect, right? So that you can look at individual connections, right, that may be meaningful, or you can just sort of say, hey, what's the average connectivity of the default mode network here? We have 0.62, which is, that's pretty good. It's pretty high value and not unexpected. So that is something we can use. We're going to use in the next tutorial. We're trying to compare what's different about the default mode network across participants. So and another way to estimate connectivity is saying, I want to know about this node here specifically and how it's connected with the rest of the brain. That's called seed to voxel. We take one region we call a seed. In this case, we're going to take the posterior cingulate cortex, this coordinate here. We're just going to extract that time course for that and compare it to how the time course across the entire brain at the voxel level, and just see what sort of seems to pop up as being most relevant for how they're related to each other. Similar process that we did before, and you were able to dig in these more if that interests you. But at the end of the day, the payload here is that we just want to see what the data looks like at this individual level. And as you can see, we define this node, the PCC. We have various regions here that are voxels, right? They can be defined as different regions. Positively correlated, negatively correlated, and we can use this to compare across participants as well. That we will in the next tutorial. Similar to the task stuff, I just show a demonstration of how we can extract where those regions tend to be, which ones the peaks stat for those are, et cetera. If you want to report those, if you're, it would be most meaningful, you're looking across participants at this point, right? But this is just at the individual level. We're not making any inferential statistics. We're just saying, hey, what's going on with this one participant? Okay, so that's what first level estimation for connectivity would look like. It's maybe how you would approach it if you're looking at fMRI data within the NiLearn universe here in Python. But obviously, we want to move from this and make some inference on what's going on, how the brain relates to behavior, some phenotype, etc. So we'll do this in the last and final tutorial that we have. At the second level, we're again going to estimate individual connectivity and compare across participants. But for the sake of this tutorial, I'm only going to look at average connectivity of the default mode network and average connectivity of the posterior cingulate cortex. I'm not going to do whole brain stuff. I'm going to skip over that because typically when I do the sort of analyses, we use like machine learning approaches, and that just hasn't been covered yet in this series. I think it would be quite an undertaking to talk about that and brain data in the same talk for one tutorial. So we'll skip over that for now. But I hope that you'll get some, idea of what's going on here, how we may approach connectivity for group inference. So we start again. We're downloading multiple participants this time. We got 20 here. And this data doesn't have a phenotype measure to it. So what I did is I simulated a phenotype. I just said, hey, here's just some numbers here. Give me some value for these participants. We can call that anything we want. I didn't place any more constraints on it. I just said, I just estimated it. So I'm going into too much detail on that. And we're going to do two sorts of analyses on these first. One is the continuous, saying like how does the phenotype relate to this brain data? And then we're going to use a grouping variable here in this data. They coded gender as a binary variable, and we're just going to use that as like sort of a group variable. It's the only one I saw in that data. I could have estimated one, but we're going to use that for now. I'm not sure how they measured it, but they put it as dichotomous, and we'll use it for demonstration purposes. All right, so first, given that we're going to look at the default mode connectivity, similar to what we did before, this is something we saw in the last tutorial. We're going to define these regions, we're going to extract those time courses, and we're going to look at how this relates to our given phenotype, right? So first, we extract cross participants, and this is just one individual, this is multiple participants. So one of the things I did here is I just want to see what's the connectivity, what's the distribution of connectivity for each individual that we have. And we have quite a bit of variation here. Some are pretty low, some are relatively high, right? We have a decent distribution here with adequate variance to kind of look at what may be going on. And running a second level analysis, given that we extracted the average connectivity for the default mode network, it's just one variable, right? It's relatively simple. We're just running a regression on that variable. And we're trying to predict connectivity in default mode network on average, right? The average connectivity for each participant based on their phenotype. So we include the phenotype here, I add a constant to our regression, and we fit the model. And we have a negative trend, right, for our phenotype, but it's not significant. Okay. So that's just showing you what that would look like there if we're looking at that. But is average default mode network connectivity really the most meaningful metrics that we want to look at? Right? There's a lot of different connections in the default mode, and it could be different. So here, one of the things I did to investigate this a little further is I said, hey, how does our phenotype relate to every connection in the default mode network? And I extract that for each connection, and I look at that, extract those values, and I place that within a plot that I have here. I'm just saying, how does connectivity relate to this phenotype for each connection? And you see a very different picture, right? And just for comparison, I have the entire sample where we have all the positives here that we expect, right? We see a very different relationship here. This is probably just a good case study for saying, especially in the brain, but maybe items that you're looking at and self-report measures could be something meaningful in the individual things that make up that huge parcel that you're making, right? You're saying, I just want to know about default mode network connectivity. Well, it appears that there's something meaningful in the different connections that we have here. And if we can contrast that with the average sample, we do see that the average sample has more connectivity between the posterior cingulate cortex and the left angular gyrus here. And the phenotype seems to have a stronger connectivity, right, between this medial prefrontal cortex and this right angular gyrus or temporal brow junction. I'm not sure what we called it here. So this was a real analysis. Obviously, I'd want to dig into that a little more, run some additional tests, try to see what most meaningfully characterizes that phenotype, right? There might be something really important there versus just average default mode network connectivity. And we use this binary gender variable that they have just to compare across participants. And we don't have anything significant here. Again, there's a slight positive trend though. And just to plot it and see, there's a lot of overlap here. These results aren't exciting at all. They weren't intended to be. This is just for demonstration purposes at this point. But as you can see, there's a lot of overlap. It appears that this group here has a little bit more, a little bit higher distribution, a little higher up than this one. There's so much overlap here in this Violin plot that, it makes sense that there's not a meaningful distinction between those. This is just a regression that I ran with both gender and phenotype. Still remain not significant. There's many different extensions you can have to this that you can include. We had a really good presentation on the mediation moderation. Those would apply here as well. A lot of statistical approaches that you're familiar with, you could incorporate into these sorts of analyses. We have the same thing here for C-divoxyl. Here we did the same thing we did before, just define a posterior cingulate cortex region, seeing how it relates to voxel across the entire brain, and then just average it just to see, what's the average posterior cingulate cortex connectivity across the brain. Now, we both know, looking at the last tutorial, that not every region of the brain was positively connected or negatively connected with the posterior cingulate cortex. So averaging across that might miss some meaningful things there, right? But this is just demonstration at this point. Obviously, you could dig in that a little more further. But we have a similar pattern here where we don't have a significant association with phenotype or our binary gender variable, or when we add them together. So I didn't take the time to make these statistics significant to make it maybe more exciting for some people, but that's science, right? Okay. So very broadly, you should have a sense for how what we're measuring fMRI, the different data types that we have, as well as some very broad statistical approaches that hopefully have inspired you to think about other ways you can design studies or run analyses that could answer maybe more complex questions or important questions specific to your area. All in all, this is a good basis that I can do within a 90-minute period to sort of talk about these. But of course, I welcome questions or any areas of interest that maybe people may have and digging into every component of these first analyses. So with that, I'll open it up for questions.
Hi, Drew. First off, I would like to say thank you for questions and for your presentation. It was really good. And I guess one of my questions is when working with like all this different technology, especially like in the beginning, like what advice do you have for people who are just starting off kind of learning this kind of information? Yeah.
Yeah, it helps. So it really helps to have working with a lab that works with specific tools that we have. This is a very growing area. There's new tools all the time, and they pop up and they're very popular for a year, then they're no longer used a couple of years later. So it is kind of challenging. It does border on the sort of tech component of keeping up with that sort of thing and what's relevant and new. So if that's something that you're interested in, this might be a good field for you. If not, you should hire somebody who maybe is more interested in those things, right? But it is quite daunting, and you have to accept that and be willing to struggle through it a little bit. I mean, we struggle a little bit. We ask help from others, those sorts of things, and you eventually get to a place where I think if anybody that's learned R or any statistical language, it was pretty hard at first, and then all of a sudden it's like, I think I kind of get it, and then you realize I don't get it at all, and then the next day you're like, oh, I get it again. It's like that whole thing, only maybe for multiple different tools, right? So yeah.
Thank you. I know Annie said that, like, so some part of it's going to be recorded if you have questions. And then if you don't want questions, I don't have host access right now, but we can just like cut off that part when we like release it out to the public.
I think I might have it. I see a thing that says recording right here. I could push stop if I wanted to.
Oh,
Is that
perfect
me?
then.
Okay, sure. I've never had host privilege before. This is the first for me. Okay. So do you want me to stop it now and allow for maybe other questions? Or?
Yeah, if no one else has questions that they want recorded, I think stopping it now works perfectly.
Going in 1, 2, 3. Okay.